3I-ATLAS just accelerated in ways that defy the physics textbook. It brightened when it should have dimmed. It turned blue when everything about it should have remained red. And just days ago, literally days ago, it vanished behind the sun. But now it's back. And what we're seeing is raising questions nobody's rushing to answer. Something happened during that passage, something NASA detected, something astronomers are still struggling to explain. You're watching this on November 4th, 2025. You're one of the few people actually paying attention to what's unfolding. While millions scroll past space news without a second glance, you're about to examine data that challenges fundamental assumptions about how objects move through our solar system. This isn't speculation. This isn't fringe theory. This is confirmed observation from multiple institutions: NASA, the European Space Agency, observatories across 3 continents, all documenting behaviour that shouldn't be possible according to our current understanding of gravitational mechanics. Here's what happened. On October 29th, 2025, at exactly 11:15 Universal Time, 3I-ATLAS reached perihelion. That's the closest point to the Sun in its trajectory 130 million miles away, moving at 42 miles per second. For context, that's fast enough to cross the United States in less than a minute. During this approach, multiple observation systems were tracking every measurement, every shift in velocity, every change in brightness. And what they recorded wasn't just unusual, it was impossible by conventional physics. Some orbital analysts have proposed non-gravitational acceleration, measurements that NASA has flagged for closer investigation. Think about what that phrase actually means. Non-gravitational, meaning this object sped up beyond what gravity alone would cause. Imagine a car on cruise control driving through a tunnel. Suddenly, it accelerates without anyone touching the gas pedal, without any visible force acting on it. That's what 3I-ATLAS did near the Sun. It gained velocity in ways that violate the predictions of our most advanced orbital mechanics models. But here's where it gets stranger. The comet brightened unexpectedly. Comets typically brighten as they approach the Sun because heat causes their icy surfaces to sublimate. That's when ice transforms directly into gas without becoming liquid first. But the brightness curve of 3I-ATLAS didn't follow standard patterns. It brightened too early, too intensely, and in spectral wavelengths that don't match typical cometary outgassing. Multiple observatories flagged this anomaly independently. Lowell Observatory in Arizona, the Neil Gehrels Swift Observatory, ground-based telescopes across Chile and South Africa, all documenting the same impossible behaviour, and then there's the colour. Comets approaching the Sun typically become redder. The heat releases dust particles that scatter light in red wavelengths, giving them that characteristic rusty glow you see in telescope images. But 3I-ATLAS turned blue. Not slightly blue. Distinctly, unmistakably blue. That coloration suggests ionized gases, carbon monoxide, perhaps, or other volatile compounds being ejected at high velocity. But the spectral signature doesn't quite match known outgassing patterns. It's close, but not identical. Close enough to be intriguing, different enough to be confusing. Think about this for a moment. What accelerates an object beyond gravitational prediction? What causes a comet to brighten in non-standard patterns? What makes it turn blue when physics says it should turn red? These aren't rhetorical questions designed to sound mysterious. These are genuine puzzles that astronomers are actively working to solve right now, today, in real time. Here's the timeline. 3I-ATLAS approached perihelion throughout late October. Observatories tracked it as closely as Earth's position allowed. Then, on October 29th, it swung behind the Sun from our perspective. For 3 days, direct observation became nearly impossible. The Sun's glare, the positioning geometry, the sheer intensity of solar radiation overwhelmed most detection systems. It was like losing a radio signal when you drive through a tunnel. You know the object is still there, still moving, still following its trajectory, but you can't see it. You can't verify what's happening during those critical hours when it's closest to the Sun, when the most dramatic changes typically occur. And then, on November 1st and 2nd, it reappeared, post-perihelion, moving away from the Sun, heading back toward the outer solar system on its hyperbolic trajectory, meaning it's never coming back. This is a one-way path through our cosmic neighbourhood. Chi-Cheng Jiang at Lowell Observatory captured the first optical image after perihelion on October 31st. And what that image showed raised more questions than it answered. The comet was still there, still intact, still exhibiting the same blue coloration, still demonstrating characteristics that don't fit comfortably into standard comet models. What happened during those 3 days behind the sun? What changed while we couldn't watch? What forces acted on this object during its closest approach to our star? You need to understand something. NASA doesn't flag non-gravitational acceleration lightly. When space agencies document behavior that contradicts orbital predictions, they've already ruled out measurement error, instrumentation drift, atmospheric interference, and dozens of other potential false positives. They've checked the math multiple times. They've cross-referenced with other observation systems. They've consulted with astrophysicists who specialize in cometary dynamics. And still, the data doesn't match expectations. Still, something about 3I-ATLAS defies conventional explanation. Now, before we go deeper, before we break down exactly what these measurements mean, and why scientists are racing to understand them before the December observation window closes, I need you to do something. If you're ready to examine what most people are ignoring, hit that like button. Not because I'm asking, but because you're signalling that you're here for actual investigation, not surface-level headlines. Drop a comment telling me where you're watching from. That's not just engagement, it's community building. Thousands of people are tracking this in real time, connecting data points, sharing observations. You're part of that network now. And if you haven't subscribed to stay updated on 3I-ATLAS findings, now's the moment. Because what we discover in the next 45 days will determine whether this remains a curious anomaly or becomes something far more significant. Let me be direct with you. This isn't sensationalism. This isn't clickbait dressed up as science. These are documented observations from credible institutions using professional-grade equipment and peer-reviewed methodologies. The acceleration anomaly is real. The unexpected brightening is confirmed. The blue coloration is verified across multiple independent observation systems. What remains unclear is what these anomalies actually mean. What they tell us about the nature of interstellar objects, about the physics of cometary behavior, about the potential for phenomena we haven't yet categorized or understood. We're standing at a specific moment in time, November 4th, 2025, with 3I-ATLAS now visible again, now accessible to observation, now moving through a trajectory that will bring it closest to Earth on December 19th. That's 45 days away. 45 days to gather data, to analyze spectral signatures, to confirm or rule out competing hypotheses. After that, 3I-ATLAS becomes too faint, too distant, too difficult to observe with the precision this mystery demands. So here's where we begin, not with speculation, but with evidence, not with wild theories, but with documented facts that happen to be deeply strange. We're going to examine what NASA actually detected, what the European Space Agency is tracking right now, what Harvard astrophysicist Avi Loeb noticed that mainstream coverage missed. We're going to look at the timeline, the measurements, the competing interpretations, and we're going to do it without jumping to conclusions, without dismissing anomalies just because they're uncomfortable, and without accepting explanations that don't actually explain the data. The question isn't whether something unusual is happening. Multiple observation systems confirm that it is. The question is what that unusual behavior actually tells us, and whether we're willing to follow the evidence wherever it leads, even if it challenges assumptions we've held for decades about how objects move through space, about what's natural versus artificial, about the difference between familiar phenomena and genuinely unprecedented observations. October 29th wasn't just another perihelion passage, and what we're about to explore together will show you exactly why that matters. You already know 3I-ATLAS arrived from beyond our solar system. You know it was discovered back in July, that it's the third confirmed interstellar object ever detected, that its trajectory marks it as a visitor from another star system entirely. We're not rehashing that history. You didn't come here for a recap of July headlines. You came here because something changed. Something shifted between summer discovery and October passage, and that shift is what matters now. Here's what you need to understand about rarity. 3 interstellar objects. That's the confirmed count in all of human astronomical observation. 1I/Oumuamua in 2017, flying through before anyone realized what they were seeing. 2I/Borisov in 2019, captured beautifully, studied extensively, fitting almost perfectly into standard comet models. And now 3I-ATLAS in 2025, arriving with characteristics that don't match either predecessor. 3 objects out of billions of stars, trillions of possible trajectories, centuries of telescope technology. You're watching something genuinely rare unfold in real time. But rarity alone doesn't explain the attention. What explains the attention is behavior. 3I-ATLAS isn't just another interstellar visitor passing through quietly, following predictable orbital mechanics, behaving exactly as physics textbooks would expect. It's doing things that challenge those expectations, and those challenges intensified dramatically during its perihelion passage. From July through September, observations were routine. Standard astrometric measurements: position, velocity, brightness, trajectory confirmation. Multiple observatories tracked it as it fell sunward, accelerating under gravitational influence exactly as predicted. The European Space Agency's JUICE spacecraft, currently on its mission to Jupiter, allocated observation time to 3I-ATLAS, taking advantage of its unique position to gather data from angles Earth-based telescopes couldn't access. Ground-based systems in Chile, South Africa, Australia maintained regular monitoring schedules. Everything looked normal, everything fit expectations. Then came October, and with October came changes. The first anomaly appeared around October 15th, roughly 2 weeks before perihelion. Brightness measurements began deviating from predicted curves. Not dramatically at first, just enough to make astronomers double-check their calibration, verify their instruments, rule out atmospheric effects or temperature fluctuations in their detection systems. But the deviation persisted, and it grew larger as the comet approached the Sun. By October 25th, 4 days before perihelion, the brightening had become undeniable. This wasn't instrument error. This wasn't atmospheric interference. This was real physical change happening to the object itself, change that couldn't be fully explained by standard cometary sublimation models. The brightness increased too rapidly, in spectral bands that didn't perfectly match the expected signature of dust and ice vaporization. And then came the acceleration anomaly. NASA's orbital tracking system's sophisticated mathematical models that predict object positions down to meter-level accuracy started showing deviations. Small at first, within the margins that could be attributed to outgassing pressure, to material ejecting from the comet's surface and creating tiny reactive forces. But the magnitude of acceleration exceeded what outgassing alone should produce, based on the comet's size and estimated composition. Something was pushing 3I-ATLAS beyond what gravity and known physical processes would predict. This is where mainstream coverage stops. This is where most articles say scientists are studying it and move on to the next headline. But we're not doing that, because what happened next during perihelion passage and immediate post-perihelion observation is where the mystery deepens from mildly unusual to genuinely confusing. On October 29th, 3I-ATLAS reached its closest approach to the Sun and simultaneously became invisible to most Earth-based observation. The geometry was brutal. From our perspective, the comet passed almost directly behind the Sun, its position overwhelmed by solar radiation, its faint light drowned in the glare of our star. For 3 days, October 29th through October 31st, direct optical observation became nearly impossible. Radio telescopes could still track certain signatures. The Neil Gehrels Swift Observatory, working in ultraviolet and X-ray wavelengths, maintained some detection capability. But visual confirmation, spectral analysis, detailed morphological observation, all of that went dark. Think about what that means. The most critical phase of cometary passage, when the object experiences maximum heating, maximum sublimation, maximum physical stress, happened behind a curtain we couldn't penetrate. We lost surveillance exactly when surveillance mattered most. It's like watching a detective story where the camera cuts away during the crucial moment, then returns to show the aftermath without revealing what actually transpired. But space agencies weren't completely blind. ESA's JUICE spacecraft, positioned differently in its trajectory, maintained observation capability throughout most of the perihelion window. NASA's Swift Observatory captured data in non-visible wavelengths. Radio telescopes across multiple continents tracked emission signatures that penetrate solar interference, so we didn't lose all information. We just lost the clearest, most direct observational access exactly when it would have been most valuable. And when 3I-ATLAS reappeared on November 1st and 2nd, when Lowell Observatory captured those first post-perihelion optical images, astronomers immediately noticed the changes. The blue coloration was stronger, more pronounced. The brightness remained elevated beyond prediction. The coma, that fuzzy cloud of gas and dust surrounding the nucleus, showed structural asymmetries that didn't match standard outgassing patterns. Something had changed during passage. Something had happened during those 3 invisible days. This is where we are right now, on November 4th, 2025, with an interstellar object exhibiting behaviour that doesn't fit comfortably into existing models, with observation data that raises more questions than it answers, with a scientific community actively working to understand what they're seeing before the December window closes and 3I-ATLAS becomes too faint to study effectively. What we're about to examine together isn't speculation about what might have happened during those 3 invisible days, but rather what the actual measurements tell us, and more importantly what they don't tell us. October 29th, 2025, 11:15 Universal Time. 3I-ATLAS reached perihelion at a distance of precisely 1.36 astronomical units from the Sun. That translates to 210 million kilometres, or if you prefer miles, 130 million, roughly the distance between Earth and the Sun, but measured from our star to this interstellar visitor at its moment of closest approach. The comet was travelling at 68 kilometres per second, 42 miles per second, fast enough to cross the continental United States in under a minute, fast enough that relativistic effects, while negligible, start becoming mathematically relevant in high-precision calculations. This wasn't just another astronomical event logged in observation databases. This was the critical moment when months of anticipation converged into hours of intense data collection. Every major observatory capable of detecting 3I-ATLAS had allocated observation time. Every space agency with relevant instrumentation had coordinated tracking schedules. Because perihelion is when comets reveal their true nature. The intense solar heat strips away surface materials, exposing subsurface composition. Outgassing accelerates dramatically, creating visible comas and tails that tell stories about chemical makeup and structural integrity. If 3I-ATLAS was going to behave like a standard comet, perihelion would confirm it. If something unusual was happening, perihelion would expose it. The approach vectors were calculated months in advance. Astronomers knew exactly when 3I-ATLAS would reach perihelion, knew its speed and trajectory down to fractional percentages, knew what brightness they expected based on size estimates and albedo measurements. This is routine astrophysics, orbital mechanics refined over centuries, computational models validated across thousands of cometary observations. When you know an object's mass, trajectory and distance, you can predict its behaviour with extraordinary accuracy. Usually. But 3I-ATLAS had already started diverging from predictions weeks before perihelion. That October 15th brightness anomaly wasn't isolated. By October 20th, the acceleration measurements were showing consistent deviations. Not wild swings, not random fluctuations, systematic, progressive changes that suggested real physical processes acting on the object beyond simple gravitational influence. NASA's Jet Propulsion Laboratory, which tracks near-Earth objects and interstellar visitors with meter-level precision, flagged these anomalies in internal reports. The deviations were small enough to be attributable to outgassing if the comet was actively sublimating, but large enough to require explanation. Then came the visibility problem. As 3I-ATLAS approached perihelion, its position from Earth's perspective moved closer to the Sun's angular location in our sky. By October 28th, one day before perihelion, the comet was positioned less than 30 degrees from the Sun as seen from Earth. That's roughly the width of 3 fists held at arm's length, close enough that observing it required telescopes to point dangerously near the Sun, risking instrument damage from scattered solar radiation. By October 29th, during actual perihelion passage, the comet passed almost directly behind the Sun from our viewpoint, becoming completely invisible to standard optical telescopes. Imagine tracking a suspect vehicle through city traffic, only to have it enter a tunnel exactly when you need to see what happens next. You know it went in, you know it should come out the other side, but what happened during transit remains invisible. That's the situation astronomers faced on October 29th. The most critical phase of cometary behaviour, maximum heating, maximum sublimation, maximum structural stress, occurred behind a solar curtain that blocked direct observation. But space agencies had anticipated this. NASA's Neil Gehrels Swift Observatory, operating in ultraviolet and X-ray wavelengths, maintained partial observation capability throughout perihelion. These wavelengths penetrate solar glare more effectively than visible light, allowing detection of emission signatures from gases ejected by the comet. And what Swift detected was fascinating. Hydroxyl gas OH molecules, the telltale signature of water sublimating from ice. This confirmed that 3I-ATLAS contained water ice, as expected for a comet-like object, but the hydroxyl emission was stronger than size estimates suggested it should be, indicating either that the comet was larger than calculated or that sublimation was more vigorous than predicted. ESA's JUICE spacecraft, positioned differently in its Jupiter-bound trajectory, had angular separation from the Sun sufficient to maintain observation throughout most of the perihelion window. JUICE's instruments captured data from October 27th through November 1st, providing crucial coverage during the invisible period. This multi-platform observation strategy ground telescopes when possible, space-based systems when ground observation failed, meant that astronomers weren't completely blind during perihelion. They just lost the clearest, most detailed observational capability exactly when it mattered most. And during this passage, something changed. The data from SWIFT and JUICE showed brightness variations that didn't follow standard sublimation curves. The spectral signature shifted toward bluer wavelengths, indicating increased emission in shorter wavelengths of light, typically associated with ionized gases or hot materials. The acceleration anomaly, tracked through radio position measurements, persisted through perihelion and actually intensified near closest approach. Whatever was causing the non-gravitational acceleration became more pronounced when 3I-ATLAS experienced maximum solar heating. Think about what that timing suggests. Standard cometary outgassing does produce non-gravitational acceleration material. Ejecting from the surface creates reactive thrust like a natural rocket engine. But the magnitude of acceleration detected on 3I-ATLAS exceeded what its estimated mass and surface area should produce through normal outgassing. Either the comet was ejecting material far more vigorously than its size would predict, or something else was contributing to its acceleration beyond simple gas pressure. October 31st brought the first post-perihelion optical image. Qicheng Jiang at Lowell Observatory in Arizona captured 3I-ATLAS as it emerged from solar glare, now positioned sufficiently far from the Sun's angular location to allow safe telescope pointing. And that image revealed a comet that looked different from its pre-perihelion appearance. The coma was larger, more diffuse, indicating active outgassing as expected after solar heating. But the coloration was distinctly blue, not the reddish-brown of dust-dominated comets, not the neutral white-grey of gas-dominated objects, but a pronounced blue tint that suggested specific chemical processes. Blue coloration in comets typically indicates carbon monoxide emissions or other volatile compounds being ionized by ultraviolet radiation. But the spectral signature wasn't a perfect match for known CO emission patterns. It was similar, close enough to be the leading explanation, but with subtle differences that left room for uncertainty. Some wavelengths were stronger than expected, others were weaker. The overall pattern suggested ionized gases, but the exact chemical composition remained ambiguous, and the acceleration anomaly persisted post-perihelion, as 3I-ATLAS moved away from the Sun on November 1st and 2nd, continuing its outbound trajectory on the hyperbolic path that would carry it back to interstellar space. Orbital tracking systems continued detecting velocity changes beyond gravitational prediction. The non-gravitational acceleration was decreasing as the comet moved farther from solar heating, which made sense if outgassing was the cause. Less heat means less sublimation, means less gas pressure, means less thrust. But the rate of decrease didn't perfectly match outgassing models. It was close, but not exact. This is the pattern you need to recognize. Everything about 3I-ATLAS is almost explained by standard comet behavior. Almost. The brightness is mostly explained by sublimation, except for the timing and magnitude. The acceleration is mostly explained by outgassing, except for the intensity and trajectory. The blue color is mostly explained by ionized gases, except for the spectral discrepancies. Each individual anomaly could be dismissed as measurement uncertainty or modeling imprecision. But taken together, they form a pattern of near explanations that don't quite resolve into comfortable certainty. What happened during perihelion on October 29th? We know the physical trajectory. We know the measurements collected by partial observation systems. We know the post-perihelion appearance. What we don't know with absolute certainty is why those measurements don't align perfectly with predictions. Why a comet that should behave like 2I/Borisov, the last interstellar comet, which followed standard models almost perfectly, is instead behaving like something familiar but subtly wrong. And that subtle wrongness is what makes this fascinating, and that wrongness is what we're about to examine in detail. Let me show you what the data actually reveals. Not interpretation, not speculation, just the raw observational facts that multiple institutions have confirmed independently. Because what makes 3I-ATLAS genuinely intriguing isn't any single anomaly. It's the accumulation. It's the way each unusual measurement compounds the previous one, building a picture that becomes harder to dismiss as simple measurement error or modelling imprecision. Start with the non-gravitational acceleration. NASA's orbital mechanics team detected this first, around October 20th, roughly 9 days before perihelion. When you track an object's position over time with sufficient precision, you can calculate its velocity and acceleration with extraordinary accuracy. You know where it was. You know where it is. You know where it should be based on gravitational forces, and when an object appears somewhere other than where gravity alone would place it, that's non-gravitational acceleration. This happens with comets routinely. Outgassing creates thrust. As frozen materials sublimate into gas and escape the comet's surface, they push against the nucleus, creating a reactive force, Newton's third law, in action. Every action has an equal and opposite reaction. Gas escaping in one direction pushes the comet in the opposite direction. Astronomers account for this in orbital calculations, adding outgassing parameters to their models based on estimated comet size, composition, and distance from the Sun. But here's what's unusual about 3I-ATLAS. The magnitude of acceleration exceeded what its estimated size and composition should produce. Think about it like this. Imagine you're pushing a car. The amount of force you can generate with your muscles determines how much the car accelerates. If the car accelerates more than your pushing force should allow, something else must be contributing thrust. That's the situation with 3I-ATLAS. The acceleration detected was larger than outgassing alone should produce based on the comet's estimated mass. Now, there's an obvious counter-explanation. Maybe the mass estimate was wrong. Maybe 3I-ATLAS is smaller than astronomers calculated, meaning the same outgassing force would produce more acceleration. Or maybe the comet is more volatile rich than expected, ejecting more gas per unit of solar heating than standard models predict. Both possibilities are on the table, both are being investigated, but neither quite resolves the discrepancy completely, because the acceleration profile, how it changed over time as the comet approached and then receded from the Sun, doesn't perfectly match outgassing curves. Notice how these timeline details align. The acceleration anomaly appeared October 20th. 9 days later, on October 29th, the comet reached perihelion. The acceleration peaked during closest approach, exactly when solar heating was maximum. That timing fits outgassing perfectly. But the magnitude during peak doesn't fit the estimated mass, and the decay rate post-perihelion is slightly faster than outgassing models predict. Slightly, but measurably. Now layer in the brightness anomaly. Around October 15th, 5 days before the acceleration anomaly appeared, 14 days before perihelion 3, ZAS-ATLAS began brightening faster than predicted. Cometary brightness follows well-understood patterns. As distance from the Sun decreases, surface temperature increases, sublimation accelerates, more material enters the coma, and the comet brightens. Astronomers can predict this curve with high accuracy based on size, albedo, composition, and trajectory. But 3I-ATLAS brightened early and intensely. By October 25th, 4 days before perihelion, it was noticeably brighter than models predicted, not wildly so, but enough that multiple observatories confirmed the discrepancy independently. Lowell Observatory in Arizona, the European Space Agency's tracking network, amateur astronomers with sophisticated equipment across 3 continents, all documenting the same phenomenon, brightness increasing beyond prediction. And then there's the spectral signature. This is where it gets technically fascinating. When you analyze light from a comet through a spectrograph, you see discrete emission lines, specific wavelengths, corresponding to specific elements and molecules. Hydrogen emission, oxygen emission, carbon monoxide, sodium. Each element produces a unique spectral fingerprint. By measuring which wavelengths are present and how strong they are, astronomers determine composition. 3I-ATLAS showed strong hydroxyl emission OH molecules, indicating water ice sublimation. That's expected. Standard comet behavior. But the emission intensity was stronger than the comet's estimated size would predict. Either the comet is larger than calculated, or it's sublimating more water per unit area than typical comets. The Neil Gehrels Swift Observatory detected this during perihelion passage when optical telescopes couldn't observe directly. Swift's ultraviolet instruments captured hydroxyl signatures that confirmed water ice presence, but raised questions about quantity. And here's where the colour mystery enters. Most comets approaching the Sun become redder. Solar heating releases dust particles from the nucleus along with gases. These dust particles scatter sunlight, and the scattering preferentially affects shorter wavelengths more than longer ones, a phenomenon called Rayleigh scattering. The same physics that makes Earth's sky blue and sunsets red. For comets, increased dust means increased red coloration, giving them that characteristic rusty appearance in photographs. But 3I-ATLAS turned blue. Distinctly, measurably blue. That coloration indicates ionized gases dominating over dust. Specifically, it suggests carbon monoxide or other volatile molecules being excited by ultraviolet radiation and emitting light in shorter wavelengths. This happens with gas-rich comets that have relatively little dust. But here's the puzzle. The spectral lines don't perfectly match known carbon monoxide emission patterns. They're close, very close, but with subtle differences, some wavelengths stronger than expected, others weaker, creating a signature that's almost but not quite carbon monoxide. Some researchers have proposed ionized carbon compounds, perhaps from organic materials being broken down by solar radiation. Others suggest unusual gas-to-dust ratios that create atypical scattering. Harvard astrophysicist Avi Loeb, who's studied interstellar objects extensively since Oumuamua, noted in recent comments that the blue coloration combined with non-gravitational acceleration creates an intriguing profile. Not conclusive, not proof of anything extraordinary, but intriguing enough to warrant careful analysis. Now let me show you how these anomalies connect. The brightness increased October 15th. The non-gravitational acceleration appeared October 20th. Both intensified as the comet approached perihelion on October 29th. The blue coloration became pronounced during and after perihelion passage. The hydroxyl emission detected by Swift was stronger than expected. The spectral signature was almost but not quite standard carbon monoxide. Each data point is individually explainable through conventional comet physics, with some parameter adjustments, but together they form a pattern that's harder to dismiss. Pattern recognition is crucial here. Imagine a puzzle where each piece almost fits. The shape is close, the colours nearly match. You can force the pieces together with a little pressure. But when you step back and look at the complete picture, something feels wrong. The image is distorted, the connections unnatural, the overall pattern subtly incorrect. That's what astronomers are experiencing with 3I-ATLAS. Every measurement almost fits standard models. Almost. And this is precisely where mainstream coverage stops. Articles report, comet passes through solar system and move on. But we're not moving on. Because the accumulation of near explanations that don't quite resolve into certainty is what makes this scientifically fascinating. When one measurement defies expectations, you question the measurement. When multiple independent measurements all defy expectations in related ways, you question the model. ESA's JUICE spacecraft has been conducting a dedicated observation campaign from November 2nd through November 25th, gathering detailed spectroscopic data from angles that Earth-based telescopes can't access. That campaign is ongoing right now, as I'm speaking to you on November 4th. The data being collected in real time over the next 3 weeks will either confirm conventional comet explanations with adjusted parameters, or it will deepen the mystery by revealing additional anomalies that standard models can't accommodate. What's at stake here isn't whether 3I-ATLAS is unusual. Multiple institutions have confirmed that it exhibits non-standard behaviour. What's at stake is whether that unusual behaviour can be explained within our current understanding of cometary physics, or whether it requires us to expand that understanding, to add new categories, to acknowledge phenomena we haven't previously encountered or properly documented. The non-gravitational acceleration, the unexpected brightening, the blue coloration that doesn't quite match known emission lines, the hydroxyl intensity exceeding size-based predictions, the timing of these anomalies correlating with perihelion passage, the persistence of acceleration post-perihelion at rates that don't perfectly match outgassing decay models. These aren't wild speculations or fringe observations. These are documented measurements from NASA, ESA, Lowell Observatory, Neil Gehrels Swift Observatory, amateur astronomers with professional-grade equipment, all converging on the same conclusion. Something about 3I-ATLAS doesn't fit comfortably into existing frameworks. And what makes this even more compelling is what's missing from the conversation. what mainstream science reporting isn't emphasizing, and what the December observation window might finally resolve or further complicate. Here's a question that demands an answer. Why is a space agency that can photograph galaxies 13 billion light-years away struggling to image a comet 126 million miles from the Sun? NASA has captured detailed images of Pluto's surface from 3 billion miles away. The James Webb Space Telescope resolves individual stars and galaxies so distant their light has been travelling toward us since shortly after the Big Bang. Hubble routinely images Neptune's atmospheric storms and Jupiter's volcanic moon Io with stunning clarity. Yet 3I-ATLAS, relatively nearby in cosmic terms, remains frustratingly difficult to observe with the detail these anomalies demand. The technical explanation is straightforward. 3I-ATLAS is small, estimated somewhere between 1 and 3 kilometers across, though those estimates carry significant uncertainty. Small objects reflect very little light. At 126 million miles during perihelion, and now closer to 150 million miles post-perihelion, the comet appears as a faint smudge even to large telescopes. Its brightness is measured in magnitude 12 or 13, too faint for naked eye observation. Visible through amateur telescopes with dark skies and patience, but not bright enough for the casual spectacular photography that made comets like Hale-Bopp or Neowise famous. Add to that the speed. At 42 miles per second during perihelion, 3I-ATLAS was moving fast enough that long-exposure photography, the technique used to capture faint objects by accumulating light over time, becomes complicated. The comet moves noticeably during exposure, creating motion blur that reduces image sharpness. Short exposures avoid blur but capture less light, producing dimmer images. It's a technical trade-off that makes detailed observation genuinely challenging. And there's the sun glare problem we've already discussed. From October 28th through November 1st, the comet's position from Earth's perspective was too close to the sun's location in our sky to allow safe direct observation. Pointing a telescope near the sun risks catastrophic instrument damage sensors designed to detect faint starlight can be permanently destroyed by scattered solar radiation. So during the most critical observation window, when perihelion passage was occurring and the most dramatic changes were happening, direct optical observation became nearly impossible. But here's what's interesting about these limitations. Other observatories succeeded when NASA struggled. Lowell Observatory captured the first post-perihelion optical image on October 31st. Amateur astronomers with sophisticated equipment have been tracking 3I-ATLAS since early November and posting observations to online forums and research databases. The European Space Agency's JUICE spacecraft maintained observation capability throughout periods when Earth-based systems couldn't. So while observation is challenging, it's not impossible. It just requires the right instruments at the right angles with the right timing. What this creates is an information gap. Not a conspiracy, not a cover-up, but a genuine technical limitation that prevents the kind of comprehensive, continuous, high-resolution monitoring that would definitively answer many questions about 3I-ATLAS's behaviour. We have snapshots. We have partial data from different instruments operating in different wavelengths. We have enough information to document anomalies, but not enough to definitively explain them. And this is precisely where mainstream media coverage falls short. Most articles simplify the story to interstellar comet passes through solar system, without addressing the measurement discrepancies that make this passage scientifically intriguing. They mention the discovery, note the perihelion date, perhaps include a quote from an astronomer saying we're studying it closely, and then move to the next story. What they don't do is examine the data. What they don't explain is why the data doesn't quite fit standard models. What they don't acknowledge is the genuine scientific uncertainty that makes this worth paying attention to. You need to understand something about institutional scientific communication. Space agencies like NASA are conservative by necessity. They don't announce extraordinary findings until they've exhausted conventional explanations. They don't speculate publicly about unusual possibilities until they've confirmed measurements multiple times through independent systems. They don't want to be the agency that cried paradigm shift, only to discover it was instrument error or modelling oversight. So their public statements remain measured, cautious, emphasising ongoing study rather than definitive conclusions. But that caution creates a vacuum. When mainstream sources say scientists are studying it, without explaining what makes it worth studying intensely, when they report anomalies without contextualising why those anomalies matter, people assume nothing significant is happening. The story gets buried beneath more dramatic headlines, political controversies, natural disasters, economic shifts, because space news without clear implications feels abstract and distant to most audiences. Yet for those paying attention, for those examining the actual observation reports rather than press releases, the picture is more complex. The non-gravitational acceleration flagged by NASA isn't mentioned in most mainstream articles. The unexpected brightness curve documented by multiple observatories gets simplified to "comet brightens as expected." The blue coloration that doesn't quite match known emission signatures becomes "comet displays typical gas emissions." The nuance disappears, replaced by simplification that obscures what makes this scientifically compelling. Harvard's Avi Loeb has been more vocal about the anomalies than most researchers. Loeb gained attention and some controversy for his work on Oumuamua, the first confirmed interstellar object, which he argued showed characteristics potentially consistent with artificial origins. His speculations were criticised by many astronomers as premature, but his fundamental point was valid. When objects exhibit behaviour that doesn't fit natural explanations perfectly, we should at least consider all possibilities rather than defaulting to the most conventional interpretation. With 3I-ATLAS, Loeb has noted the blue coloration as unusual, the non-gravitational acceleration as requiring careful analysis, the combination of factors as potentially significant. He's not claiming anything definitive, he's pointing out that the data warrants closer examination before dismissing the anomalies as simple modelling errors. And he's right. That's not fringe thinking. That's proper scientific skepticism applied to observations that genuinely don't fit expectations perfectly. But mainstream coverage doesn't engage with that nuance. It either ignores Loeb's comments entirely or frames them as "controversial scientist proposes alternative theories," without actually examining whether his observations about the data are accurate. And they are accurate. The blue coloration is real. The non-gravitational acceleration is confirmed. The brightness anomaly is documented by multiple independent systems. Whether Loeb's interpretations of what those anomalies might mean are correct is a separate question from whether the anomalies themselves exist. And they do exist. So why isn't this bigger news? Partly because technical complexity doesn't translate well to general audiences. Partly because institutional caution prevents dramatic announcements. Partly because the story lacks clear implications, no asteroid impact threat, no mission to visit it, no obvious technological application, and partly because truly understanding what's happening requires engaging with observational data, spectroscopic analysis, orbital mechanics calculations, technical material that most journalists and readers don't have the background to evaluate critically. But for those willing to examine the evidence, for those capable of understanding what non-gravitational acceleration means, or why spectral signatures matter, the picture is genuinely intriguing. Not proof of anything extraordinary, not confirmation of artificial origins or revolutionary physics, but intriguing enough that dismissing it as just another comet misses the actual scientific story unfolding in real time. The December observation window will be critical. As 3I-ATLAS continues its outbound trajectory, visibility improves throughout November and early December. More telescopes can observe it safely. Longer exposure times become possible as it moves farther from the sun's glare. Spectroscopic analysis can be conducted with greater precision, and the data collected during this window, particularly the detailed composition measurements from ESA's JUICE campaign, will either resolve the anomalies through conventional explanations or confirm that something genuinely unusual is occurring. That resolution is coming. The timeline is set. December 19th marks closest approach to Earth, the optimal observation moment when distance is minimized and detail is maximized. After that, 3I-ATLAS continues outbound, becoming progressively fainter, eventually too dim for detailed study. The window is open now, the opportunity exists now, and whether mainstream media is covering it adequately or not, the observations are happening, the data is being collected, and the answers, or at least better questions, are approaching. What those observations might reveal, and what competing explanations exist for the anomalies already documented, is where this gets truly fascinating. Let me walk you through the competing explanations. Not to tell you which one is correct, we don't have enough data yet for certainty, but to show you why this isn't as simple as it's a comet versus it's something else. The reality is more subtle, more technically complex, and ultimately more interesting than that binary framework suggests. Start with the standard model. 3I-ATLAS is a natural comet, composed primarily of frozen volatiles like water ice, carbon dioxide, methane and ammonia, mixed with dust and rocky material. As it approaches the Sun, solar heating causes these frozen materials to sublimate directly into gas without melting. The gas escapes, carrying dust particles with it, creating the visible coma and tail we associate with comets. This process is well understood, documented across thousands of cometary observations, modelled with sophisticated physics that accounts for heat transfer, sublimation rates, gas dynamics, and dust interactions. Under this standard model, the anomalies 3I-ATLAS exhibits should be explainable through parameter adjustments. The non-gravitational acceleration? Adjust the outgassing rate upward, assume the comet is more volatile-rich than initially estimated, and the reactive thrust from escaping gases accounts for the extra acceleration. The unexpected brightness? Assume the comet is slightly larger than estimated, or has a higher albedo, or is sublimating more vigorously than typical comets at this distance. The blue coloration? Attribute it to ionized carbon monoxide dominating over dust in the coma, indicating a gas-rich composition. These explanations are reasonable. They require no new physics, no exotic materials, no departure from our understanding of how comets behave. And for most astronomers analysing 3I-ATLAS, this adjusted standard model is the working hypothesis. Comets are diverse. Each one has unique composition, structure, and behaviour. Some are dusty and red, others are gas-rich and blue, some outgas vigorously, others barely sublimate. Within the range of natural variation, 3I-ATLAS could simply represent the more unusual end of the spectrum without being fundamentally different from any other comet. But here's where doubt enters. The parameter adjustments required to fit. 3I-ATLAS into standard models are all in the same direction toward more unusual, more extreme, more atypical values. The outgassing rate needs to be higher than expected. The gas-to-dust ratio needs to be more gas-dominated than typical. The sublimation efficiency needs to be more vigorous than similar-sized comets. Each individual adjustment is plausible. But when you need to adjust multiple parameters simultaneously, all toward the extreme end of their ranges, the explanation starts feeling forced. It's like trying to explain why someone is 7 feet tall by saying they have longer legs, longer torso, longer neck, larger bones, all technically true, all individually plausible. But at some point you step back and recognize they're just unusually tall, rather than trying to explain it through component adjustments. 3I-ATLAS might just be an unusually active, gas-rich, rapidly sublimating comet without being anything more exotic than that. Now, let's examine the alternative interpretations. These aren't fringe theories or wild speculation. These are hypotheses being discussed in academic circles, albeit cautiously, because they require evidence that doesn't yet exist in sufficient quantity. First, alternative. Internal heat source. What if 3I-ATLAS contains radioactive materials or chemical reactions generating heat beyond solar radiation? Comets typically are cold objects, their interiors frozen solid until solar heating penetrates inward. But if radioactive decay or exothermic chemical reactions were occurring inside the nucleus, that internal heat could drive sublimation more vigorously than solar heating alone would predict. This would explain the elevated brightness, the strong outgassing, the non-gravitational acceleration exceeding expectations. There's precedent for this in planetary science. Jupiter's moon Europa, Saturn's moon Enceladus. Both generate internal heat through tidal forces that drive geological activity far beyond what solar heating would produce. Some asteroids may contain enough radioactive elements to generate measurable internal heat. Could a comet harbour similar processes? Possibly. It would require unusual composition, concentrations of radioactive isotopes higher than typically found in cometary material, but it's not impossible. Second alternative, fragmentation event. What if 3I-ATLAS is breaking apart, shedding material not through gentle sublimation but through structural failure? Comets can fragment under stress, thermal stress from rapid heating, rotational stress from spin acceleration, structural weaknesses from previous perihelion passages. Though 3I-ATLAS is on its first passage through our solar system, it may have passed through other stellar systems previously. Fragmentation releases large amounts of material suddenly, creating brightness spikes and strong outgassing that could produce the observed acceleration anomalies. The blue coloration might result from freshly exposed interior material, with different chemical composition than the surface. The spectral anomalies might come from a mixture of sublimation gases and fragmentation debris. This explanation requires no exotic physics, just structural failure occurring during perihelion stress. Observations in December might confirm this by detecting discrete fragments or unusual coma morphology, indicating recent breakup. Third alternative, and this is where it gets genuinely speculative artificial origin, not in the sense of alien spacecraft disguised as comet, but rather in the sense that some measured characteristics don't fit natural comet behaviour, even with parameter adjustments. This is the hypothesis Avi Loeb has explored publicly, cautiously, with significant caveats about insufficient data. The reasoning goes like this. If non-gravitational acceleration exceeds what outgassing can produce based on estimated mass, and if alternative natural explanations like internal heat or fragmentation don't perfectly fit the observations either, then you're left with a possibility of propulsion beyond natural gas release. That could mean an internal process we haven't considered, a physical mechanism not yet accounted for in cometry models, or most speculatively an artificial system. Loeb points to the blue coloration as potentially significant if it doesn't match natural emission patterns perfectly. He notes the acceleration profile as requiring explanation beyond standard outgassing. He suggests that technological signatures, if they exist, might appear exactly like what we're seeing, an object that almost fits natural explanations, but maintains subtle anomalies that resist complete resolution. Now, before anyone jumps to conclusions, let me be absolutely clear. There is no confirmed evidence of artificial origin. None. What exists is observational data that doesn't perfectly fit standard models, combined with the scientific principle that when conventional explanations don't quite work, you should at least consider alternatives rather than forcing the data into frameworks that require multiple simultaneous adjustments. That's not proof. That's intellectual honesty about uncertainty. The artificial hypothesis faces enormous burden of proof. Extraordinary claims require extraordinary evidence, and right now the evidence is merely unusual rather than extraordinary. The blue coloration is almost explained by carbon monoxide. The acceleration is almost explained by outgassing. The brightness is almost explained by size and albedo adjustments. Almost. The question is whether those almost explanations are close enough to settle the matter or whether the remaining discrepancies justify deeper investigation. Some claims circulating online are not scientifically verified. There are reports of radio signals at 1420 MHz, following mathematical patterns supposedly detected from 3I-ATLAS. These remain unverified, unsupported by any peer-reviewed publication or official observatory announcement. Similarly, theories about mothership with probe release or structured object disguised by outgassing are speculative constructs from online communities, not scientific hypotheses with observational backing. These should be clearly distinguished from the documented anomalies NASA, ESA and professional observatories have actually confirmed. What we know from confirmed observations, non-gravitational acceleration beyond standard outgassing predictions, unexpected brightness curve, blue coloration with spectral signatures close to but not perfectly matching carbon monoxide, hydroxyl emissions stronger than size estimates suggest. These are real. These are documented. These require explanation. What remains uncertain, whether those explanations exist within conventional cometry physics with parameter adjustments, whether they require expanding our models to include processes we haven't adequately considered, or whether they point towards something genuinely unprecedented that doesn't fit into existing categories at all. And here's the critical nuance. You can take this data seriously without jumping to extraordinary conclusions. You can acknowledge that the observations are unusual without claiming they prove anything beyond natural phenomena. You can maintain scientific skepticism about exotic explanations, while also maintaining skepticism about forcing conventional explanations that require multiple simultaneous adjustments to fit the data. What would settle this? Detailed spectroscopic analysis showing exact chemical composition and confirming whether emission lines match natural processes perfectly or retain unexplained discrepancies. Mass estimation refined through additional measurements, allowing accurate calculation of whether outgassing can account for acceleration. Observation of whether the comet sheds material asymmetrically, indicating fragmentation, or maintains structural integrity throughout observation window. Detection of discrete fragments if breakup is occurring. Confirmation or refutation of internal heat through thermal imaging if such observations become possible. The December observation window offers opportunity for some of these measurements. ESA's JUICE campaign, running through November 25th, is gathering detailed spectroscopic data. Ground-based telescopes have improving visibility as 3I-ATLAS moves farther from the Sun's glare. December 19th's closest approach to Earth provides optimal viewing geometry for mass estimation and morphological analysis. If the comet is fragmenting, December observations should reveal structural changes. If internal heat is driving unusual activity, thermal measurements might detect it. If it's simply an unusual but natural comet, refined measurements should resolve the anomalies within adjusted parameters. What happens if December observations deepen the mystery instead of resolving it? What if detailed spectroscopy confirms the emission lines don't quite match any known natural process? What if mass estimation rules out outgassing as sufficient explanation for acceleration? What if no fragmentation is detected despite the unusual activity? Then we're left with a genuinely unprecedented object requiring explanations that current frameworks don't easily accommodate. That's not a prediction, that's a possibility. The more likely outcome is that December data will refine our understanding, adjust parameters appropriately, and confirm 3I-ATLAS as an unusual but ultimately natural comet, remarkable in its characteristics but not revolutionary in its implications. But possibility matters. The fact that we can't yet definitively rule out alternatives, that the data maintains ambiguity despite months of observation, that multiple independent institutions have documented behaviour requiring explanation, that makes this worth following closely. Not with wild speculation, not with certainty about exotic origins, but with genuine scientific curiosity about an object that refuses to fit neatly into the categories we've spent centuries refining. And that brings us to why the next 45 days are so critical, why December 19th matters so much, and what we should be watching for as this observation window unfolds. We're working against a clock now, not in any dramatic must-solve-the-mystery-before-disaster strikes sense, but in a very practical observational sense. 3I-ATLAS is moving away from the Sun and Earth on its hyperbolic trajectory, becoming progressively fainter, eventually too dim for the detailed study these anomalies demand. The window of opportunity is open now. It will remain open through December. After that, the comet fades into observational obscurity, leaving whatever questions remain unresolved for the indefinite future. Right now, on November 4th, 2025, 3I-ATLAS is positioned roughly 150 million miles from Earth and moving outbound. It's visible through amateur telescopes from the Northern Hemisphere, not easy, but accessible to anyone with reasonably dark skies, moderate equipment, and patience to locate it. Professional observatories are tracking it continuously, gathering spectroscopic data, monitoring brightness changes, measuring velocity with increasing precision as more observations accumulate. Early December brings a significant visibility improvement. As the comet moves farther from the Sun's position in our sky, the angular separation increases, allowing safer and more comfortable observation without risk of scattered solar radiation damaging instruments. Longer exposure times become possible, capturing fainter details in the coma structure and potential tail formation. Multiple observatories worldwide can coordinate simultaneous observations, gathering data from different angles and instruments to build comprehensive analysis. December 19th, 2025 marks closest approach to Earth, 167 million miles, roughly the distance between Earth and the Sun. That's the optimal observation moment. Minimum distance means maximum brightness, maximum detail, best opportunity for high-resolution imaging and spectroscopy. If 3I-ATLAS is fragmenting, December 19th, observations should reveal structural changes, discrete pieces separating from the main nucleus, asymmetric coma patterns indicating directional material release. If internal processes are driving unusual activity, detailed thermal imaging during closest approach has the best chance of detecting temperature anomalies. What exactly are scientists looking for? Several specific measurements will help resolve the current anomalies or deepen the mystery further. First, mass estimation refinement. The non-gravitational acceleration question hinges partly on accurate mass. If the comet is smaller or less dense than current estimates suggest, outgassing could plausibly produce the observed acceleration without requiring alternative explanations. Improving mass estimates requires measuring how the comet responds to gravitational forces, how its orbit deviates from pure gravitational prediction, and how that deviation correlates with solar heating. December observations, combined with data already collected, will refine these calculations substantially. Second, composition analysis through detailed spectroscopy. The blue coloration and spectral line ambiguities need resolution. Is the emission pattern truly carbon monoxide with unusual intensity ratios, or is something else producing similar but not identical signatures? Are there unexpected elements or molecules present that standard comets don't typically exhibit? High-resolution spectroscopy during December's optimal visibility window can answer these questions definitively, either confirming conventional composition with unusual ratios or revealing genuinely anomalous chemistry. Third, outgassing pattern mapping. Does material release from 3I-ATLAS show the directional preferences typical of rotating comets with active regions on their surfaces? Or is the outgassing symmetric, suggesting uniform surface activity unusual for natural comets? Detailed imaging can map coma morphology, identifying jets or fans of material indicating localized sublimation points. These patterns tell stories about nuclear structure, rotation, and surface composition. Fourth, structural integrity assessment. Is the nucleus intact, or are fragments separating? Fragmentation would explain sudden brightness increases and strong outgassing through exposure of fresh interior materials. Observing whether the coma contains discrete condensations, bright spots indicating separated fragments, versus smooth distribution indicating intact nucleus will distinguish between fragmentation and vigorous but unified sublimation. Fifth, thermal emission measurement. Does the comet radiate heat beyond what solar heating should produce? Infrared observations during December can detect internal heat sources if they exist at detectable levels. If radioactive decay or chemical reactions are generating significant internal heat, thermal imaging should reveal it. If no excess heat is detected, internal heat source explanations become less plausible. ESA's JUICE spacecraft campaign, running from November 2nd through November 25th, is collecting data from angles Earth-based telescopes can't access. JUICE's instruments include spectrometers, cameras, and particle detectors capable of measuring composition, structure, and material release patterns. The data from this campaign, which will be analysed and published over coming months, may provide crucial insights that ground-based observation alone cannot achieve. Amateur astronomers are contributing too. The international amateur astronomy community, equipped with increasingly sophisticated telescopes and imaging systems, has been tracking 3I-ATLAS and submitting observations to research databases. This crowdsourced approach expands observational coverage beyond what professional facilities alone can provide, capturing data during moments when major observatories are pointed elsewhere, or weather prevents observation at primary sites. Think about what the next 45 days represent. Between now and December 19th, every clear night offers opportunity to gather data that might resolve these mysteries. Every spectroscopic observation refines composition estimates. Every astrometric position measurement improves orbital calculations. Every photometric brightness measurement constrains models of outgassing and sublimation. The accumulation of data from multiple sources, multiple instruments, multiple observation techniques creates a comprehensive picture that individual snapshots cannot provide. What are the possible outcomes? Several scenarios, each with different implications for how we understand 3I-ATLAS. Scenario 1. Conventional resolution. December observations confirm refined parameters that explain all anomalies within standard cometary physics. Mass estimate is revised downward, making outgassing sufficient for observed acceleration. Spectroscopy confirms carbon monoxide dominance, explaining blue coloration. Brightness curve fits adjusted sublimation models. The mystery resolves into unusual but natural comet with extreme but not unprecedented characteristics. This is the most likely outcome, the one most astronomers expect. Scenario 2. Fragmentation confirmation. Observations detect discrete fragments, structural changes, asymmetric material release indicating nucleus breakup. This explains brightness spikes, strong outgassing, unusual activity through fresh interior material exposure. The comet is fragmenting, a dramatic but entirely natural process documented in other comets. The anomalies are explained through catastrophic structural failure rather than exotic processes. Scenario 3. Expanded natural models. Observations reveal characteristics that don't fit standard frameworks, but remain explainable through natural processes we haven't adequately modelled, perhaps unusual chemical composition requiring new categories, or internal structures producing unexpected behaviour, or interaction effects with the solar environment not previously documented. The comet expands our understanding of natural variation without invoking artificial origins. Scenario 4. Persistent anomalies. December observations fail to resolve the discrepancies. Detailed spectroscopy still shows emission lines that don't quite match known processes. Refined mass estimates still leave acceleration unexplained by outgassing alone. No fragmentation is detected. No conventional explanation fits comfortably without multiple simultaneous parameter adjustments. The mystery deepens, leaving open questions that require further investigation beyond what December observations can provide. Which scenario unfolds depends entirely on what the data reveals, and that data is being collected right now, accumulating night by night as telescopes across the world point toward this small, faint, rapidly moving object at the edge of observable detail. You can participate in this observation window if you have access to telescopes. 3I-ATLAS is currently visible in the constellation Virgo, magnitude around 1213, requiring at least 6-inch aperture telescopes under dark skies. Star charts and position predictions are available through astronomical software and online databases. Photographing it requires tracking mount to compensate for motion, but visual observation is possible with sufficient aperture and dark adaptation. You're not just watching, you're contributing to the observational record if you choose to document what you see. For those without telescopes, the next 45 days offer opportunity to follow developments as professional data gets analysed and published. ESA will release preliminary findings from JUICE observations. Lowell Observatory and other research facilities will publish refined measurements. Astrophysics journals will feature papers analysing composition, trajectory and behaviour. The scientific story unfolds in real time across December, building toward whatever conclusion the evidence supports. December 19th isn't an arbitrary date, it's the geometric optimal point when Earth and 3I-ATLAS reach minimum separation. After that, distance increases, brightness decreases, observational detail diminishes. By January, the comet becomes significantly fainter. By February, it fades beyond reach of all but the largest professional telescopes. By March, it's effectively gone from observable reach, continuing outbound on its interstellar trajectory, departing our solar system as mysteriously as it arrived. This is the window. These are the days. What we learn or fail to learn in the next 6 weeks determines whether 3I-ATLAS becomes a footnote in astronomical catalogues or a case study requiring deeper investigation. The clock runs regardless of what we want. The comet continues its trajectory regardless of whether we've solved its mysteries. Observation requires action now, analysis before the opportunity vanishes, answers before the evidence fades beyond reach. And that urgency is precisely why what happens between now and December 19th matters so profoundly for understanding what 3I-ATLAS actually is. So what is 3I-ATLAS? The honest answer, right now, on November 4th, 2025, is we don't know with absolute certainty. We know it's an interstellar object on a hyperbolic trajectory, meaning it came from beyond our solar system and will return to interstellar space. We know it exhibits characteristics that almost but don't quite fit standard cometary models. We know multiple independent observation systems have documented anomalies requiring explanation. What we don't know is whether those explanations exist comfortably within conventional frameworks, or whether they point towards something requiring us to expand our understanding. And that uncertainty is valuable. Not because uncertainty feels good, it doesn't. Humans naturally crave resolution and closure, but because uncertainty that persists despite rigorous observation often indicates genuine complexity worthy of deeper investigation. When simple explanations don't quite work, when refined models still leave discrepancies, when multiple expert institutions document the same anomalies independently, you're looking at something real, something that matters, something deserving continued attention rather than premature dismissal. This is what informed observation looks like, not jumping to extraordinary conclusions based on insufficient evidence, not dismissing anomalies because they're uncomfortable or inconvenient to existing models, but rather maintaining careful balance between skepticism of exotic claims and skepticism of forced conventional explanations, following evidence wherever it actually leads, even if that destination remains uncertain. The December observation window will provide crucial data. ESA's JUICE campaign, Ground-Based Spectroscopy, Amateur Contributions to Observational Databases, December 19th, Closest Approach Measurements. All of this accumulating evidence will either resolve the current mysteries through refined parameters or deepen them through persistent discrepancies. We'll know more in 6 weeks than we know today. The question is whether more translates to settled or more complicated. What should you watch for? What developments would indicate movement toward resolution versus continued ambiguity? If detailed spectroscopy matches known emission patterns perfectly with adjusted parameters, conventional explanation is confirmed. If mass estimates reconcile acceleration with outgassing predictions, non-gravitational anomaly is resolved. If fragmentation is detected, brightness and activity anomalies are explained. These would be signs that 3I-ATLAS fits natural comet frameworks after all, remarkable in characteristics but not revolutionary in implications. If spectroscopy continues showing near matches that don't quite align, if acceleration remains unexplained by refined outgassing calculations, if no fragmentation appears despite unusual activity, if composition analysis reveals unexpected elements or ratios, then the mystery persists beyond December. That wouldn't prove anything extraordinary, just that we don't yet have adequate natural explanations for observed behaviour. And here's what makes this scientifically compelling, rather than mere speculation. The data is public. ESA publishes observation results. NASA releases orbital tracking information. Professional observatories share spectroscopic data through research databases. Amateur astronomers post images and measurements. You can verify the claims being made. You can check whether the anomalies are real or manufactured. You can follow the evidence yourself rather than trusting interpretation from any single source, including mine. This is collaborative investigation happening in real time. You're not a passive audience watching a story unfold, you're part of the observer network documenting an ongoing phenomenon. Your attention matters, your critical thinking matters. Your willingness to examine evidence without predetermined conclusions matters. Because science advances through exactly this process: observation, measurement, analysis, refining understanding when data demands it. Tell me in comments what you think is happening. Not wild speculation, but reasoned interpretation of the data we've examined together. What explanation seems most plausible given the evidence? What additional observations would help distinguish between competing hypotheses? Where are you watching from? What equipment do you have access to? Are you able to observe 3I-ATLAS yourself during December? These questions aren't rhetorical. The comment section is where real discussion happens, where informed observers share perspectives, where community knowledge accumulates beyond what any individual can contribute alone. Thousands of people are following this story. You're among them. The collective intelligence of engaged, thoughtful people examining the same evidence often produces insights that solitary analysis misses. Avi Loeb wrote something relevant about Oumuamua that applies equally to 3I-ATLAS. The worst-case scenario is that we detect something extraordinary and dismiss it as ordinary, because we're unwilling to consider possibilities outside familiar frameworks. He's right. Premature dismissal is as intellectually dishonest as premature acceptance. The proper stance is uncertainty that admits what we don't yet know, while continuing to investigate what we can measure. What happens after December? If mysteries persist beyond the observation window, if questions remain unresolved when 3I-ATLAS fades beyond detailed study, those questions don't vanish. They become part of the research agenda for future interstellar objects, for improved detection systems, for theoretical work modelling exotic scenarios that current frameworks don't accommodate. One object doesn't settle fundamental questions, but it opens them, creating space for deeper investigation that might not otherwise occur. And here's what's genuinely exciting about our current moment. We live in an era when interstellar objects are becoming detectable. Oumuamua in 2017 was first, Borisov in 2019 was second. ATLAS in 2025 is third. Improved telescope systems, automated detection algorithms, dedicated sky surveys mean more will be found. We're transitioning from interstellar objects are theoretical to interstellar objects are observable, to eventually interstellar objects are common enough to study systematically. Each detection teaches lessons. Oumuamua taught us interstellar objects can have unexpected shapes and acceleration characteristics. Borisov taught us some interstellar comets behave exactly like solar system comets. ATLAS is teaching us well. We're still learning what ATLAS teaches, but it's adding to our understanding of natural variation, cometary behaviour, observational challenges, and the importance of not assuming all interstellar visitors fit neat categories. The real story here isn't mysterious object defies explanation, but rather careful observation reveals complexity requiring thoughtful analysis. That's less dramatic, but more accurate. That's less satisfying to our hunger for definitive answers, but more honest about the process of actual science. That's what separates informed investigation from sensationalism. Before December 19th arrives, stay engaged. Follow observation reports as they're published. Watch for ESA's preliminary findings from the JUICE campaign. Check whether refined spectroscopy resolves or deepens composition mysteries. Monitor whether closest approach observations detect fragmentation, structural changes, or continued unexplained behaviour. The answers, or at least better questions, are coming. And if you haven't already, subscribe to stay updated on 3I-ATLAS developments. Hit the notification bell so you don't miss analysis of December observations when they arrive. Share this video with people capable of engaging thoughtfully with technical content, not to spread alarmism, but to expand the community of informed observers tracking this story as it unfolds. The story isn't over, the data is still accumulating, the observation window is still open. What we discover or fail to discover in the next 45 days will shape how we understand this object, how we approach future interstellar visitors, how we balance conventional frameworks with willingness to consider alternatives when evidence demands it. 3I-ATLAS is active again after perihelion. It's visible again after vanishing behind the sun. It's observable again during the crucial window when answers might finally emerge. The acceleration anomaly remains. The blue coloration persists. The spectral mysteries continue. The December deadline approaches. And whatever resolution comes conventional or unprecedented will arrive, because observers like you chose to pay attention, while others looked away. Keep watching. The sky has more to tell us. And sometimes, just sometimes, what it tells us is stranger than anything we expected to hear.